Hello everyone. So in this lecture we'll start our discussion on molecular reaction dynamics, meaning how reactions happen and what are the dynamics of reactions, how molecules come close together and then they form the products from reactant to product. Now there are two approaches to understand this process. Fundamentally, everything is based on collisions between reactant molecules, but we already covered a great deal of the collision theory, how reactions work, in the earlier course, and which can be found in any standard textbook. And briefly, what you do there is you first calculate the number of collisions between, say, two species A and B per unit time and per unit volume. And then what you do is that those number of collisions will give you a reaction, but of course not all collision gives you reaction, because when you collide, there is a collision between two molecules. We know that every reaction has an activation barrier, so you have to cross a certain amount of energy, and then you very cleverly insert that concept, introduce that concept that you have to cross this barrier, energy barrier, in order to the reaction to happen, and then what you do is that you use your collision theory, as well as you use the Maxwell distribution of molecular speed. You convert it to energy distribution, because you have to consider statistical distribution of energies among all these reactant species. And then you can arrive at a formula which we'll discuss briefly when we compare with what we are going to do right now later. So, and that formula satisfactorily explains many gas phase reactions, although it slightly actually always overestimates the actual rate constant that you get from using this formula, and that what you actually get from experiments. Now, to understand how reactions work, what we are going to do is that we actually want a formula of rate constants, how it varies with temperature, and initially, so as I said, there are two approaches. One is the collision based approaches, and the other one which we are going to discuss is based on something which is based on potential energy surfaces. Now, what is potential energy surface and how it is connected to the reaction dynamics, that we are going to discuss. And so first we will understand what is potential energy surface. Now, potential energy surface means, if I suppose have two atoms, let's start with atoms. Suppose if I bring two atoms closer together, so how the potential energy between them is changing if a bond is being formed. And that all of you know that we can form a diatomic molecule, and the molecular potential energy looks like as an anharmonic potential energy surface, which in the close to the ground state you can approximate as a harmonic potential. Now, this is how it looks like. So, this is basically, suppose if I have A and B, two molecules, and I am talking about the internuclear separation, meaning let me draw it like this. Suppose this is A atom and this is B atom, and we are talking about this distance, which is known as the internuclear separation. So, separation between the nuclei of these two atoms, which is plotted along which is along this direction, along x-axis, and along y-axis we are plotting the potential energy as they are brought closer together. Now, we see that the potential energy falls and it goes to a minimum at a critical distance, which we call as Re. So, Re is known as the equilibrium bond distance between these two atoms, which is between the two nuclei of these two atoms. And then if you further push this atom together, what will happen? The electrons in the atoms will try to repel each other, and the potential energy again goes up. So, at this point we say that a bond has been formed between, it's a diatomic molecule potential. But of course, this R equilibrium and the bond length is not always constant at R equilibrium, because the bond always vibrates, as we discussed. So, around this equilibrium position we will always see a vibration depending on the amount of energy that the molecule has. Suppose the molecule at a particular time has this much energy. So the amplitude of the vibration will be something like this. If it has a higher energy, it will have a higher vibration. So you have all these vibrational energy levels, and if you approximate with a harmonic oscillator, you know that harmonic oscillator's energy levels are equispaced. So this is the energy and this is the bond distance, and at this distance I call it as the equilibrium bond distance. Now here the zero of energy, the way the curve on the left is shown, the zero of energy is choice of zero of energy is very arbitrary. So here it is chosen that when these two atoms are infinitely separated or far apart, there is no interaction between them. At that point, when r is going to infinity, that energy it is chosen to be 0. Now also there is something called dissociation energy. It basically tells you how much energy you have to supply in order to bond for the bond to break. So that is known as dE. But dE, when you measure this bond dissociation, you always get something lower than dE. The reason is that this dE is measured from the bottom of this potential well, but you know that always for a harmonic oscillator or for an anharmonic oscillator, the lowest even at the lowest quantum number v equal to 0, you have a 0 point energy. So you do not start from here when you measure the dE, rather you actually start from slightly above, and that we call as d0. So d0 is always magnitude wise lower than dE. Now these are all these details for a diatomic molecule, and then there is a very interesting history how all these quantum mechanics of molecules emerged. And as you know that around 1925 the quantum mechanics was developed independently by Schrodinger and also later by Heisenberg and many others. Now so first quantum mechanics are basically the time dependent Schrodinger equation and its time independent version came. And then around 1927 or so, two scientists, Hitler and Fritz London, they actually proposed something like, suppose quantum mechanics told that what is the structure of atom, because if you have read some or studied some basic quantum mechanics, you know that atoms and molecules energy levels are quantized, and what Schrodinger gave is electronic structure for the hydrogen atom, and which he could successfully explain the atomic spectra which was observed experimentally. And he basically rediscovered the Bohr frequency condition, and but he showed that the quantum numbers actually come out very naturally as a solution of differential equation, and moment you put some boundary conditions to it. Now after that, Hitler and London asked what is the change that happens when you talk about hydrogen molecule from hydrogen atom. So let's say I have an hydrogen atom, okay, so and I just denote it like this. So it has a nucleus and it has an electron cloud around it, and then I'm now talking about H2 molecule. And Hitler and London basically asked what happens if I just bring these two molecules closer together, what will be the energy of these two. Now what they interestingly figured out, there is something called an exchange force that happens between these two, in the sense that you can think that I have, say, atom A and atom B, both are hydrogen atoms, and I have, say, electron 1 and electron 2. What they showed, actually the total wave function can be written, of course, as a product of the two individual atoms wave function, and then they showed that, okay, I have electron 1 in A and electron 2 in B, but there will be also another contribution that electron, when the bonding is formed, or the bonding happens, so electron 2 goes to atom A and 1 goes to atom B. So meaning actually they are as if exchanging the electrons, the atoms are exchanging the electrons. So this was their formulation about the total wave function of the molecule. And then eventually Linus Pauling subsequently said that You can also have something known as ionic contribution. Ionic contribution in the sense the two electrons are in the same atom, meaning suppose if I let's say I'm just writing these C's are basically the coefficients of the wave functions, of the relative amplitude of these wave functions, and suppose I write it as C3 or whatever, and then what I'm saying that both the electrons are basically belong to atom A. You can also think that both the electrons belong to atom B. So in that sense, these two wave functions are called ionic wave functions. So sometimes people write it as a psi covalent plus psi ionic, something like that. And the potential energy for this system will look exactly like what is drawn here. And with this ionic and covalent part of this wave function, or covalent contributions of the wave function, Heitler, London and Pauling very accurately or near accurately discussed, derived the energies and equilibrium bond distance very correctly. So when you actually compare all these theoretical results with experiment, you always compare with two things. You always see what is the RE that you are calculating from your theory and match with your experiment, and the second thing is of course the dissociation energy which you figured out experimentally, what is the bond dissociation energy. Now after that the question was, suppose I have hydrogen atom and from that I constructed hydrogen molecule, and I know how the interatomic potential varies as a function of interatomic distance or internuclear distance. Now the question is, what happens if I actually bring another atom to this system? Meaning now I am talking about a hydrogen atom and then bringing it together towards an hydrogen molecule. Now this is a complicated problem because if you think that if you talk about interatomic potential, now if you have a two particle system, the total number of degrees of freedom will be 6. Now you can think that there will be 3 translational degrees of freedom of the two particle system as a whole. Well, the center of mass of this two particle system moves. There will be some rotational motion, but the rotation does not change the internuclear distance. So there will be two kinds of rotation for a linear because it's a diatomic molecule, it's a linear molecule, and then can be vibration. So there will be 3 translation, 2 linear and 1 vibration, because the total degrees of freedom for a diatomic molecule two particle system is 6. Now there is only 1 vibration, but moment you keep a third molecule together, the total degrees of freedom is 9. Now 3 goes to translation, 3 goes to rotation if it approaches as a nonlinear fashion, like 2 molecules are here and the third molecule is coming like this. But if it is linear, you will still have 2 rotation degrees of freedom. So I'll have 3 translation or 2 rotation, or 3 translation and 3 rotation, and in this case I'll have 3 vibrational degrees of freedom. In this case I'll have 4 vibrational degrees of freedom. So the number of degrees of freedom going to this interatomic thing which is connected to the vibration is actually increasing from 1 to 3 or 4 depending on what fashion you are bringing this third atom to this diatomic system. Now the question was, if I bring it, even if I bring it like in a collinear fashion, how the potential is going to change? And that was a question that Fridge London asked, I think sometime back in 1930s or so. And then it was a very interesting, there is a very interesting story, and there was a conference to honor Arnold Sommerfeld, who actually was an atomic physicist and who contributed a lot in our understanding towards atomic structure. And in that evening talk, Fridge London actually gave this proposal or asked this open question, left this open question, that what will be the potential energy diagram for a 3 particle system or 3 atomic system. And around in the sometime later, so 2 scientists, Henry Eyring and Michael Polanyi. They actually, I think, yeah, it's Polanyi, or the spelling will be Polanyi. I'll just check and update in the note in the accompanied notebook. So Henry Eyring and Michael Polanyi, so they actually came up with the idea of the potential energy surfaces, which together is known as London Eyring Polanyi surface, or LEP surface. Now the question is, what is how the potential energy surface will look like? Now you can think of this potential energy surface very interestingly. Now on the left I have actually shown you how the potential energy surface look like, but let us try to understand from where it came from. Now think about it. Fundamental to our understanding is the diatomic potential, and already we know that that potential will look like something like this if I vary the distance between A and B. Say A and B are my two molecules, something like that. Now suppose I am actually bringing a third atom, which is C, towards then A and B, and then I can think about a reaction where this AB bond gets broken and this BC bond gets formed. So I am talking about atom diatom reaction in a collinear fashion. So what are the examples? You can think about like this: two hydrogen atoms are there, and then one hydrogen atom is coming, and then you are forming another hydrogen molecule and hydrogen atom. Now if you see look at this reaction, it looks that as if there is nothing has happened, because it was H2 plus H and you are getting H2 plus H again. But this is very different, because if you label these atoms, it was A, this was B, and this was C. Now what happened is that you sorry, in this case we'll have the, instead of this BC bond, here actually you will have BC plus A, because the A bond is breaking. And then if you think, if you can label the hydrogen atoms, it will be something like HBC and HA, because the HA-HB bond is getting broken. So this is also a reaction, although apparently it doesn't look like a reaction, because it is H plus H2 giving you exactly the same thing, H2 plus H. Now the interesting thing is that so we are saying that there is already a diatomic molecule, and then another molecule, another atom is approaching, so that they form a bond. Now for this molecule AB, I'll have a diatomic potential like this. For this molecule BC also, I'll have a diatomic potential like this. And what we are going to do right now is to plot the potential energies along two different axes, meaning I'll have two different axes. On one axis I'll just plot the AB distance, and in the other axis I'll plot the BC distance. Now this is how we are going to draw it. So we are going to draw the same diagram, but there are a few things that I want to discuss, so that's why I'm redrawing it, just to make sure that the concepts are clear. And let us just try to draw it. First let us say that, okay, so we can draw it like this. You can first draw a hexagon like this, okay, and then let us draw a surface like this. Okay, so what you can see here, I have say this surface of a cube, and what I am saying here, on this surface I am basically drawing the potential energy for say AB molecule. Now AB molecule in the sense that now look at this diagram and try to connect it with this diagram. So this is potential energy for AB. So the energy is increasing in the vertical direction. Now what is this axis? So this axis now is basically the distance between AB. So this is the zero distance when there will be a huge repulsion, and this is basically the equilibrium bond distance for the AB molecule. So along this axis I am actually plotting RAB. Similarly, on the other axis, I can plot the other potential energy surface, which is basically the BC thing. And suppose the BC also has some, it's a similar potential energy, something like this. So along this direction, I'm plotting RBC. So the parallel to this is this. So I can say that this is basically showing you the BC bond vibrations. And then you can say that, okay, fine, how the potential energy looks like when I am in between. Now you see the drawing on your left, which is a more accurate or more more picturesque drawing, and what it shows is that I have a potential energy like this for the BC vibration, and I have a potential energy like this, which is a diatomic potential, which is the AB vibration, and together suppose there is actually a surface when I am varying RAB and RBC together. Okay, but now this is a collinear reaction, so that's why we are talking about only two distances. It is something like ABC, so it's suppose C is at the middle. Either you can vary this guy AB, and you can vary this thing. Now when you reach at this point, which is at this point, you can think that here along this RAB, the bond has basically dissociated, where actually I am here. So it's a potential minimum, and then it goes towards the right. So at a very asymptotic distance, you can see that it is basically A plus B isolated. But if you follow the BC bond vibration, according to that, this bond corresponds to B plus C, because the BC bond has totally dissociated. So here, this point on this energy surface is known as basically three isolated atoms together. Now we can have a better picture in here. So here actually, instead of H plus H2, they actually reacted with something like F plus H2. This is not a symmetric reaction like H plus H2. This is a kind of asymmetric collinear atom and diatomic reaction, but it is still collinear atom, which is fluorine atom, and diatomic molecule, which is H2, that kind of reaction. And of course the potential energy will be slightly different, because as you can see that HF has a much deep potential energy than basically H2. Okay, so it's kind of asymmetric, there is asymmetry in the picture, but the picture is the same. Now the question is, the question Eyring and Polanyi was asking after they had basically came up with the idea of potential energy surface. I'm still not okay with the spelling. So then they asked this question, okay fine, what is the path followed when this reaction happens, this kind of reaction, or in any general, when this kind of reaction happen? I have initially probably we started with AB, so I have AB plus C, and how I am getting this reaction. So during the course of the reaction, what happens? Now you can think I can actually break the AB bond completely, so that I have A plus B plus C, and then I can actually join the BC together. So the path will be something like that. I was here, and then I come to here, and then I come to here at this point, where actually I have A plus B plus C. In this case it is F plus H, and then again I form a molecule here. Let us actually show it on the other diagram. So one path could be like this, and then going to the other way. So we are actually talking about AB to BC reaction. So we actually start from here, and then we go from here, and then we end up in here. So we are starting from the AB well, and then going to the BC well through intermediate, where actually you dissociated all the atoms together. So basically you had A plus B plus C. But this will be very much energetically unfavorable, because as you can see here on the potential energy surface, you could actually use some other alternate path where the energy is not so high, because as you can see this is a very high energy. What we could alternately do, and what Eyring and Polanyi argued, is that you could actually follow a path which is much less in energy, and then you could actually go from this portion, say this was our starting point, to this portion of this surface. So instead of totally dissociating the atoms, you could actually do what is that when the BC bond is being formed, the AB bond is being broken. So the AB bond is not completely broken when the BC bond is getting formed, and vice versa. So what they said, that this path that going to ABC, it doesn't occur because actually it's a very highly energetic path. Rather what you have is that you have a kind of intermediate, although we will make a distinction that it's not an intermediate. Why it's not an intermediate? You have formed something like ABC kind of adduct, where neither the AB bond is broken completely nor the BC bond has formed completely. So it is partially broken AB bond and partially broken BC bond, and then you eventually break the AB bond and form the BC bond, and that structure lies somewhere here, which is shown like HHF here, but we'll use a kind of dotted thing here because it's not exactly HHF, H bonded to, because it's not it's a loose bonding or loose interaction. Now if I follow this path, I will energetically favor the reaction, because I am to dissociate the AB completely and then forming the BC actually is a much more energetic process. So this path is a minimum energy path, and they said, Eyring and Polanyi, that the reaction will proceed through an minimum energy path from say AB to BC. So that's how we got the concept of minimum energy path. Now along this minimum energy path, you will encounter a point where I have a situation that it is right at the middle, in the sense that when I am traversing this potential energy surface, so I am making sure that every time actually my energy is minimum across the motion. Let me give you a more better example. So this is another way of looking at the path where we are talking about. So actually I am traversing from say AB to BC, and on the potential energy surface I could actually go from here to here. So that's a much more energetic path. I'm not doing that. Rather what I'm doing is that I'm just following a minimum much more less energetic path, which is like this. So there is a curved surface like this, and what I'm doing is that I'm actually following the minima of this curved surface. But there's an interesting thing. When you go along this curved surface, suppose I'm drawing it once again, suppose this is the surface, what you see here is that minima, in the sense that at any point if you look around, you will see that you are sitting at the minima in the potential energy in the other direction. Other direction means along this direction, along say I'm moving in this direction, but in the other direction I'll always see that I am sitting at the minima of the potential energy surface. So that's why it is called a minimum energy path. But then at certain point you can see that this path has a maximum energy, but it is maximum along the path where we are doing this reaction, where we are basically proceeding for the reaction to happen, but that path is always minima in the other direction. So this means this is a surface, you can think of like this. You take a tube, suppose I take a tube, something like that. Now I am saying that you cut the tube along this length, you just cut it into a half like this, and what will look like is something like this. What will be left to it? So you have a tube and then you cut it, and then what I am saying, now you bend the tube. So if you bend the tube, now it will look like something like this. Let me first draw it. So it will be like this. Now you see that if I now move along this tube, what I am seeing here is that at every point I am at the minima, because I am actually following this bottom of the tube. But now since I have bent it, actually I am going through a maxima along my direction of movement. So it is minima in the sense that you are at the bottom of the tube, because the tube has a surface like this. So this is the surface, and you are always at the minima of with respect to that energy in that direction. But then I bend the tube and I am saying that I am going like this. So you will hit a point where actually you are maxima along your direction of movement, but you are at the maximum, but you are at the minimum along the other direction. Now this point is known as a saddle point. Saddle means actually if you have seen horse riding competition or something like that, you will see that there is a beautiful structure on the surface of the on top of the horse. So it's a sitting arrangement so that actually the rider doesn't fall. So basically you will have an arrangement like this, so that somebody who is actually riding the horse will not fall, because his or her legs will be on the two sides of the horse. You will have a structure like this, so that the legs are actually on two sides. But when you are moving along the length of the horse, you also have a curved surface which is like this, so that you do not move horizontally. So we have a better picture here. So this is known as a saddle. So the reaction, when it happens, it is something like this. I was in AB and I am following a path like this, and then I see that at every point I am at the minima, in the sense that it is just in a similar analogy like that curved tube. There is a curved surface and I am going through the minima of the curved surface, but then I am reaching at a point where I see that I am maxima along this dotted line, but I am at a minimum along this solid horizontal line. So that's what we actually, when you drew this potential energy surfaces, or let's say the activation energy, we said that we need a minimum energy, and we always draw this path. So this path is the minimum energy path, but you have to always remember that in all of the direction you were actually at a minimum position, and then you reach to a point where you are maximum along your direction. This is the direction of motion, but every time you are at the minima of this surface of this in any other direction. So in our tube analogy, the tube is bent like this, something like that. So this point is known as a saddle point on the potential energy surface, and the chemical species which Eyring and Polanyi talked about is a species which looks like something like this, where actually neither the AB bond has been completely broken nor the BC bond has been completely formed, and then they said that the reactants actually goes through a state which they called as a transition state. Now all we are going to do is to discuss about this transition state, how the knowledge of the transition state helps you to understand the reaction dynamics. So what they said is that around the transition state you form a kind of complex which they termed as activated complex. We'll emphasize later why it is not an intermediate. They call it as an activated complex in the sense that you activate the reactants, and then as if you form a complex where actually some bonds are weakly formed or in a state of being broken, which will eventually break as I cross this path, and that is lying at the maxima in the direction of the reaction, but in all other direction it is actually sitting at the minima of the potential energy surface. So I am at a saddle point geometry, and that state is very short lived, and that state they called as a transition state, and then they kind of visualize the transition state like this for a atom diatomic collinear reaction, where actually one bond is getting formed and one bond is getting formed, that state, this intermediate state. And then they said that I can actually calculate this rate constant, which actually Arrhenius found empirically through a series of experiments, that this is the expression for the rate constant. And then they said, in order to calculate the rate constant, all we need to know is basically the properties of this complex, or properties of this activated complex, because there are, as I said, there are two ways you can actually solve the entire process or the dynamics of the entire process by something known as collision theory, and then you can also do it by this theory, which is known as transition state theory. Now in the collision theory, the problem is that for an atom diatomic reaction or something like this, a moment you keep on increasing the number of atoms and all possible geometries of collision, then actually if you want to really calculate the rate constant, you have to solve equations of motion for each and every atom and molecules which are the reactants. Now that's a very tedious job, because you can do classical mechanics, you can use quantum mechanics, but whatever you use, your complexity is still the same, because it's a huge number of atoms and molecules you are dealing with, and the trajectories you are dealing with. So rather what you can do is that you can actually think about a potential energy surface, and you can go to a particular point in the potential energy surface. You can now visualize or get the structure on this potential energy surface, and then you can actually talk about the properties of the system, which is basically at the transition state or at the saddle point. And those properties, by properties we mean the statistical properties, which we already studied, and those properties if I know, then I can actually calculate the rate constant. And that was the entire argument of Eyring and Polanyi. So now we will see how and why basically this activated, how one can actually get an expression for the rate constant using this concept of potential energy surface. But before that, which is known as actually also the transition state theory, or in Eyring and Polanyi's language, it is also known as activated complex theory. Now before that, what we have drawn so far, if you look at it here, like say for example, we have drawn it along AB and along BC, but and it's a three-dimensional picture, but we could draw it actually along in a different way. So this is known as a projection diagram, where basically you had on the z-axis you had the energy, and then you are actually taking a projection of everything onto the xy plane, and xy plane, remember, there was only distances. So the energy you show, all this isoenergetic surface you show as a line, and this kind of diagram is known as contour diagram. Now you can see that all the points along this green line, one particular green line has the same energy, and this energy is actually increasing. So this is a different line. So moment you go from this line to that line to say this particular line to that line, your energy is increasing, and this is the reaction path coming from here to going to here. So I started from in this case actually the way it is shown, it is basically BC to AB. Now in our convention actually the reaction should be in the other direction, AB to BC. So because if you remember that this is the RAB distance, and this is suppose the equilibrium RAB distance, which corresponds to the vibration here. So in the potential energy surface, if you remember that there was something like this, and I am taking a projection, that is why you are seeing all these lines here, and then this is the BC form, and suppose this is the equilibrium distance for BC, where you see these vibrations along BC, just like the AB vibrations here. So the AB is going to BC means actually the direction of the arrow will be from here to here in our convention. or you can think of the reverse reaction also the way it is shown here. Now the point here, when you traverse this potential energy surface, you hit a maxima which is shown here, and the red spot, and this maxima is it's along the path of the reaction, but in any other direction, like the direction which I am drawing, like this vertical arrow, or horizontal, these solid red arrows, in every direction you are at the minima. So which means at this red point you are right at the top along the direction movement, and you are at the minima in the all other orthogonal direction. So you can think that this is for a very symmetric reaction. You can have an interesting situation where this barrier actually sits slightly before the symmetric point, meaning the saddle point is actually occurring slightly before. Now you can think what this is called actually early barrier. All of these are very advanced topics. I am just giving you a flavor how the potential energy surface gives you a concept of early barrier and late barrier. So if the barrier is very early, so then suppose all you have to do is to cross the barrier. Now what you can do is that, suppose you have the AB molecule initially and the C. Now there is a relative kinetic energy between these two species, AB molecule and C atom. Now this total energy between of the system you can partition as a relative kinetic energy and the vibrational energy of the AB, meaning I can have a low kinetic energy but very high vibration in the AB. Now which will help for this particular reaction? If I am going from here to here and if I encounter the barrier right before, so then it is better that I cross the barrier first. Why? Because if you have a very high vibrational energy, you can think like, suppose I am climbing a mountain like this, and then how do I do it? So it's just a straight uphill thing. So I'll just better go straight like this, because if I have too much vibrations will occur across the motion, then I may not have enough energy to cross the mountain because I have too much vibration, not too much translational energy along this direction. So I'll just bounce back from the surface, which is this blue trajectory which is shown here. So, and for an early barrier, it is better that the reactants have much more relative kinetic energy. The opposite will happen for a late barrier when the barrier is right here. So there actually what you are saying is that you are crossing the barrier, you are crossing the midpoint, but then you encounter the saddle point, and this is very interesting. If you have a high kinetic energy, what can happen is that the barrier is here, so basically you have to take a curved thing because your barrier is not at straight. You have to go like this and then you will hit the barrier. So how do you do that? One thing is that if you go straight with a very high kinetic energy, you might actually hit the wall and come back because you have to go towards left to cross the barrier. So what you can do, if you come initially with a very high vibration, then after crossing this thing you can actually convert this vibrational energy into a translational energy. So this type of barrier is known as late barrier, and for a late barrier reaction it is better that the reactants initially have higher vibrational energy than a higher kinetic energy. But these are all the details which will not go further. Our aim is very different. Our aim is to use this potential energy surface concept to understand how reactions occur. We started with a diatomic potential, and where we said that the potential energy varies some enharmonically like this, and where you can think the atoms are totally dissociated, and here you can see for a minimum energy at the equilibrium bond length you can have a diatomic potential like this. Next we said that if we have three bodies together, like AB is varying, also simultaneously I am varying BC, and then I said that okay, so the potential energy now for a two body system, as you see, it's just a line, it's a linear potential. But for a three body system, if you consider it as a collinear thing, so then you have 2 degrees of freedom because you have the AB distance and the BC distance, and then as a result your potential energy will look like a surface. So this surface we kind of tried to draw, and then we said that okay, so there is a surface like this, and then one possibility from here, say where I have AB, bound AB because it's a molecule, and in the other point it's basically BC plus A. I could actually go through this path, but that is a very high energetic path where in between I create A plus B plus C, all the atoms dissociated, but rather I could actually have this energy going from this path, which is actually a minimum energy path, because you see that everywhere along this path you are lying on the minima of the potential energy across your motion. So again, the tube analogy is a much better analogy. You can think of it like I have a tube, and then I cut the tube and I bend the tube, and then you can actually try to visualize the reaction path. So what we will do is that we will give you a video demonstration of this tube surface, so that actually you can get a better idea of the potential energy surfaces. And so the next task we are left with is to understand how one can calculate the statistical properties of this complex, which is the activated complex, and using those statistical properties how one can calculate the rate constant for the reaction, let's say AB plus C going to A plus BC. So it is atom diatom kind of reaction, and how one can get an understanding of this thing. And moment we know how to do it, we will try to actually solve a problem, very simple problem, and try to actually compare this with the collision theory. Now if we go back and have a look at the rate constant one obtained from the collision theory, you will see that it is written something like pi Bmax squared, where suppose if I have two molecules A and B, suppose this is B, this is A, and now I am talking about say collision, I am just changing the notation right now. This all we said atom diatom reaction, but now I am talking about even simpler thing, reaction between say two atoms, A and B, something like that, or two molecules, doesn't matter. So the Bmax is defined as this parameter, which is basically the addition of their radius. So that is Bmax, and then it will be multiplied by their relative velocities, and relative velocity, the expression which is obtained from Maxwell-Boltzmann distribution of molecular speed is this 8 kBt by pi mu, where mu is the reduced mass of the system, and times you will have a Boltzmann kind of factor, which is e to the power minus epsilon star by kBt, where epsilon star is the minimum energy that the collision should have to cross this barrier. You can actually have look at the derivation which is done in the earlier course. You will get the YouTube videos, or you can actually have it in your standard textbook also. Sometimes this is called as the collisional cross section, the total collisional cross section, and this is, as we said, it's basically the relative average velocity, and this is the Boltzmann factor. So if we have an expression, so this is from the collision theory, so I am just saying it is rate constant obtained from collision theory, and then we will see what is the rate constant obtained from the transition state theory, and these two should be should give me the same results. So we'll try to solve a problem where actually we'll get similar results. We should get the collision theory expression for a reaction where actually say two molecules are colliding and giving you something. Now when I say it's a two molecule, it can be atom and diatom also. So A and B notation is just arbitrary. Don't get confused with this AB plus C notation and the A plus B notation. So our AB in the old notation is basically A in the new notation, something like that. So we'll just try to solve it once we get to know what is the expression for K, or what is the expression for the K transition state theory, and use this expression to calculate a bimolecular reaction rate constants. Thank you.